Unit 2 review. All right, so for this part of the review, we're going to start with talking about quantitative and categorical variables. All right, if you remember that quantitative variables are any numbers where any arithmetic operation makes sense. So the way I kind of do is I say, if it makes sense to find the average of the numbers, then it's quantitative. All quantitative variables are numbers, but all numbers or groups of numbers are not necessarily quantitative. And I'll show you those examples here in just a second. If it's not quantitative, it's categorical, and categorical, another thing for categorical is called qualitative. College Board doesn't use qualitative, they use the word categorical, but some books use qualitative. And that is just the count, putting things in categories. So when a number is a category, that's when it's categorical and not quantitative. So for instance, zip codes. Zip codes would be categorical because it would not make sense to average zip codes. I would put in our zip code 77584, that's the zip code I live in. Maybe there's 30 people in that one. 77581, that's the one Dawson is in. Maybe there's 40 people that live in that one. Those would be categories. A list of subjects' heights. Now that's quantitative, and that's quantitative because it does make sense to find the average of heights. Times to make a buttonhole. That's quantitative because that's time, and it makes sense to find the average. The ages of several subjects. That's quantitative because it makes sense to have the average. The subjects listed according to gender. Gender would be the categories. The different gender would be the categories. Students listed by social security numbers. That would be categorical. Maybe you would say, between, if the last four digits are between 000, 0 and maybe 9, that would be all of them. 1111 or something like that, and then 1112 between 2, 3. So I don't know. Anywhere. So you have looking at the last four digits. That's categorical, and recent test scores is quantitative. Now categorical data is proportions because you think about it here. If I'm talking about subjects listing according to gender, if I said what proportion or percentage of the class are women, so using the gender of women, that would be categorical, and you would do a z-test or a chi-squared test with categorical data because that's when you use percentages versus quantitative data. That would be means or averages, right? And we did the t-test, and so that would be a one sample t, two sample t, paired t, or linear regression t. Those are all the t's. And of course, z would be one prop z, two prop z, and then chi-squared was chi-squared goodness of fit, homogeneity, or independence. All right, when you're looking at the distribution, this is a one variable distribution. Use CUS and BS. C for center, U for unusual features, and you check for gaps and outliers there. Shape is S and spread is S. Remember, when you're doing center and spread, make sure you have the context, and that's the BS. BS is be specific, and you're specific when you're giving the context. Mean is not a very resistant measure, so if you have everybody here, let's say the average of everybody's salary is $50,000, and then you have one person out here that ends up getting, let's say, $1 million. And the fact that they have $1 million means that's going to take the mean is going to be drawn to the right of the median, and it's going to be pulled toward the outlier. The median doesn't have much of a change. It's the same thing. And now if that doesn't exist and instead I have $50,000 is the median, but then one person, let's say, only makes I don't know, $1,000. Oops, sorry, that's over here. Or maybe no money, maybe they're a student or something. And then the mean gets pulled away from the median again towards the outlier. So here, the mean and the median are the same. Here, the mean is greater than the median, and here the mean is less than the median. All right, let's look at these different graphs. First of all, let's draw a frequency graph. A frequency graph is kind of like all the histograms we've seen so far. This is like, let's say 5, 10, 15. That's a frequency graph, so that's A. B, a relative frequency graph. If we did the same thing here, except instead of, this would be, let's say 30%, say that's 40%, and then that would be, that's going to be 70, so, oh, that's not going to quite add up because that's 70 already, so this would have to be like this. That would also be 30, yeah. So anyway, obviously all the percentages of the bars have to add up to a total of 100%. And finally, the cumulative frequency graph, that's also called an ogive. And we did this in test 2. And what this looked like is this. When you have a cumulative relative frequency, because it adds up to 100%, starts at 0. And if I had, let's go here, 10, 20, 30, 40, 50, maybe this is the money I've made in thousands. All right, and then I'm going to just do this. Has to be a positive slope. Let's go this way, and then, okay. So if I ask you what the median was, what you would do for median is you'd say, okay, 50%, smack dab here. You'd go here. And that's about the median. That's the median, and it's about 31, let's say. If I ask you what the IQR was, then you do 75%. Which is 45 for 75%, and then 25%. So that's Q3. Q1 is 10. And so the IQR would be 45 minus 10, which is 35. Excellent, excellent, excellent. Okay, next I want you to find the standard deviation, but I'm not going to have you, this, if you want to do it by hand, this is what the steps are by hand, but what I'd like you to do is go ahead and get your calculator out and let's put it in your calculator. 23, 36, 21, 40, 27. So let's go to our CAS here. So now let's look at the numbers. 23, 36, 21, 40, 27. Is that it? Okay, it is. Okay. All right, so you have to enter here. I'm going to just name it. I just want to name it something that it's not been named here yet. Okay, so now you're going to go to Menu, Statistics, Calculations, One Variable Statistics, One Variable OK. My X list, I'm going to put SSSD is what I labeled it as, and then OK. And there we are. My standard deviation is right here at 8.26. And that's what I got here, 8.264. If you did it by hand, you'll get about 8.234. It's close, but it's just different rounding issues. Okay, now let's look at this. For example 1, we have sample A is equal to, oh, this is the mean. The mean is equal to 7, and the standard deviation is equal to 2 for mean of A and standard deviation of A. The mean of B is equal to 5, and the standard deviation of B is equal to 3. So transform the sample A into the linear equation, 5x plus, y equals 5x plus 8. So the new mean is going to be, all you have to do is put the put the mean in here for x, and so that's where the 5 times 7 plus 8, the plus sign didn't come through the form. So that's equal to 27, but standard deviation, remember standard deviation, when I have data here, and if I have the mean and I add 8 to the mean, which is happening here, basically this is 20, right? It shifts, but the spread, and so now this is at 28, but the spread doesn't change, and that standard deviation is spread, so it doesn't change. So the plus 8, that's why you see here, all we did was multiply it by 2, and that's why it's 5 times 2. So standard deviation, the spread changes if with multiply it by 2, because here's my original one, and now I'm going to be twice as much, and then, oh boy, but let me try this again, sorry. So if this was my original spread, let's say from 1 to 5. If I multiply that by 2, now it's going to be 2 to 10. So my spread now is twice as wide. So that's why we multiply the standard deviation, so I get 10. Okay, find the mean and standard deviation of A and B when I have the mean of, A plus B, sorry. The mean of A equals 7. Oh, and not everything is on here. Okay, let me see. Let's just make some numbers up so you can, I think it's the same thing as what we're trying to, I think it's using the same, yeah, I believe so. So now it just wants us to use these same numbers that I just used, but now we're going to add A plus B. So to add A plus B, so if I'm trying to find the mean of A plus B, that's just 7 plus 5. Oh, that must be a plus sign, and that must be a 12. There we go. But the standard deviation of A plus B is going to be this here. It's going to be 2 squared plus 3 squared. Because you cannot add standard deviations, you can just add the variances. All right, let's look at the normal curve. The area under the normal curve is 1. The standard deviation under the normal curve is, for the standard normal curve, because I'm here, this is the mean is 0 and the standard deviation is 1. So the mean is 0 and the standard deviation is 1. The area under the normal curve is 1 because what it actually means is 100%. If this is all shaded, I'm saying 100% has been shaded, correct? And 100% has been shaded, but that's just in a decimal, 1. So that's why it's 1. What is the rule that describes 1, 2, 3 standard deviations from the mean? Well, let's remind you what it is. It is, 68%, 95%, and 99.7%. And what it means is that 68% of my data is within 1 standard deviation of the mean. So that's this. 95% of my data is within 2 standard deviations of the mean. And finally, 99.7% of my data is within 3 standard deviations of the mean. And that's labeled, we do, if this wasn't here, that's showing a curve here, 0, 1, 2, 3, -1, -2, -3. Okay, there's 4 basic types of normal curve problems. So this is how I'm going to have you write them out. What proportion of students view more than 6 movies per semester? So I would do this, and it's going to give me, oh yes, here we go. Students in the fine arts coming on average, so that's my mean, and a standard deviation, that's my standard deviation. So this normal model is 5 and 2. So if I were to make it, I would do 5, 7, 9, 11, 3, 1, -1. Okay, so more than 6 movies per semester, so 6 is here. So make sure that you draw this, and so I'm going to write my probability statement. It's x is greater than 6, but that's the probability that z is greater than 6 minus 5 divided by 2. To remind you how I got that, that's my observed, which was 6. That's what we found. Minus mean, was my mean, divided by my standard deviation. All right, and that's the value I'm looking for. So I'm going to, you are welcome to use a chart at that point, but I'm going to use normal CDF, and my lower bound in normal CDF is 6. My upper bound is going to be infinity. My mean is going to be 5, and my standard deviation is going to be 2. So make sure everything I write on here is something you need to write on the test. All right, so we have 6 and 5 and 2. Okay, so here I need to add a calculator page. So you're going to go menu, stats, distributions, normal CDF, and the lower bound is going to be 6. The upper bound is infinity. You can just put anything way off the chart, and the mean is 5, and the standard deviation is 2. Okay, and it's 0.30, so about 0.3085. So about of students view more than 6 movies per semester. Okay, what proportion of the students view between 3 and 8? So the drawing is now going to show the same thing. I'm not going to draw the whole thing out since I have it already drawn out nicely for me. Oh, I would want to put question mark percentage because that's the same thing I'm doing here. So the probability that x is between 3 and 8, 3 minus 5 over 2, 3 minus 9, 8 over 2. And that's what I'm looking for. So then I would just type out normal CDF, lower bound 3, upper bound 8, mean is 5, and standard deviation is 2. And I'd come to my calculator and I'd go menu stat distribution inverse norm, normal CDF. And lower bound is 3 because it's between 3 and 8. And then 5 and 2. And that's 77.45%. So I'd write about 77.45% of students view between 3 and 8 movies per semester. What proportion view less than 2? Oops, sorry, that's a 2. Probability that x is less than 2. Probability that z is less than observed minus mean divided by standard deviation. Using normal CDF. Lower bound negative infinity. Upper bound 2. Mean 5. Standard deviation 2. Okay. Menu stats. Normal CDF. Menu stats distribution, normal CDF. So negative infinity to 2. 5 and 2. And I get about 6.68%. less than 2 movies per semester. Okay. All right, and now this is the other type. So these are all normal CDFs. This one's now an inverse norm because this one gives you a percentage, and now it's asking you to find a numerical value. So there's the bottom 50%, so I have 5. So I know where that's going to be as far as, remember, 68, 95, 997. So let's look at that first. Well, that's a really ugly graph. Let's look at this one before I draw this. So remember, 68, 95, 997, here is 68. And that means the rest on the outside is going to be 16, because 16 plus 16 plus 68 is 100. And so this, we do know that it's going to be right outside, right a little bit greater than 3. So we know if this was our multiple choice, we know that it's going to be literally a little bit more than 3. So because that's 15%. And that's 3 is 1 standard deviation away from the mean. So we know that it's going to be not quite that, because at 1 standard deviation away from the mean is the 16%. Because in the 68, 95, 997 rule. Okay, so let's go ahead and write our probability statement that x is less than 3. And that's the probability that z is less than observed. Or we don't know. Sorry, I should put y here because we don't know it. Observed minus mean. Sorry. Divided by standard deviation. And we do know this percentage, and that equals 0.15. So now this is inverse norm. An inverse norm, the area is the area from the left, and that's 0.15. And the mean is 5, and the standard deviation is 2. So we're going to go to our calculator. And we're going to go to Menu, Stats, Distributions, Inverse Norm. And the area is 0.15. The mean is 5, and the standard deviation is 2. And so I get 2.9. So we knew that it was going to be right around 3. That, oh, look, I said it was going to be a little above 3. I don't know what I'm thinking, because obviously 16% is at 3. It's a little less than 16%. So, of course, it's going to be a little bit less than 3. Yeah, I spoke incorrectly there. Okay, so that's 2.9. And so about 2.9 or less movies viewed make up the bottom 15% of movies viewed. Number of movies viewed. Okay. Test A has a mean of 79 with a standard deviation of 3. Test B has a mean of 84 with a standard deviation of 5. 2 and 2. If Rudy makes an 83 on test A, I guess I should say A, and a 90 on test B, which test did he score higher to? So what we're going to do is we're going to find our z-score. So the way you're going to do that is you're going to say, okay, the z-score for A is observed. So my observed value that he got was 79 minus the mean of test A, which test A was an 83, divided by the standard deviation of 3. So 79 minus 83 is negative 4 over 3. Oh, wait a second. I completely got that opposite because he made, so it's 83 minus 79. So it'll be positive 4 over 3, which is 1.3. And the z-score for test B is going to be 90 minus 84 over 5. Yep. And that's going to be 90 minus 84 is 6 over 5. So that's going to be about 1.2. All right, and so this one you can say, hey, he did better on this one because it has a higher standard deviation, which means it's more unusual. It's further away from the mean. If we were to graph it, it would look like this. the 1.3 would be here. 1.2 would be here, and then 1.3 would be here. And you can see that this is, if this is compared to everybody else, obviously the 1.3 is higher, and it's more unusual, and it's a better score. Okay, remember on the standard normal chart, the z-score represents the number of standard deviations away from the mean. All 4-digit decimals in the middle represent the area to the left of the curve. It's talking about the z-score chart. Okay, so that is the data. That's one variable data. That's what this was, what we just did. Now we're going to do two variable data, basically bivariate data. Bi means two, and when we have an x and a y, where you have a y hat equals b naught, or excuse me, yes, b naught plus b1x, where b naught is my y-intercept, b1 is my my slope, and y is my response variable, and x is my explanatory variable. X explanatory, that's how you can remember it, explanatory. All right, now your y is going to have a hat, because the hat means prediction. Because this line that we're making, we're going to be doing linear regression. Basically, I'm doing this, and I'm saying this is my prediction line of what I'm telling you of if this is a height-weight chart of how much you'll weigh when you're a certain height. Predicted weight at a certain height. Because obviously not every, if it was perfect, then that's fine. It would be here. This is how much you are going to weigh. We could absolutely dogmatically say that. However, we can't say that because, as you can see, we have some data above, some on, and some below the line. And it's just my prediction line. Okay, so when we look at this here, we studied this scatter plot over here to the right. Remember how I put a, would it be most appropriate to move case A or case B, sorry. So case A is an outlier because it was not in the pattern of the data. You can definitely see that B is an outlier, but it is with the pattern of the data. So B is called an influential point. It's influential because it makes the slope stronger. The points obviously have a negative association because the line is negative. And the least squared regression line, remember the least squared line, that's, I'll show a demonstration for you in class, but remember that the way we did it in class is we have that this is the residual, sorry, that my picture's not great. And so the square of the residuals, your computer or calculator knows how to make the smallest area of those squares. And so that's the smallest or the least of the squares. And so that line is going to go through where it's making these squares the smallest distance. So it's the smallest area. Remember, you have a set of points, has a least squared regression line of, this should say y hat equals 2.3x plus 17. What is the residual of the actual point? Remember, residual equals observed minus prediction. I like to say actual, so I can say RAP. Residual equals actual minus predicted. So what we're going to do is the first step we're going to do is we're going to say, okay, this is my actual point. So now I'm going to say this here was my residual was 30. Once I put in 3 here. So 2.3 times 3 plus 17. And I get out 23.9. So that's my predicted. My actual, though, is 19.5. So find the residual, I put in 19.5 minus 23.9 and get 4.4. So that means that my prediction was my actual minus my predicted, because this is my actual, that's my predicted. And I have my actual minus my predicted. And that difference, that's called the residual. And that residual is 4.4, which means my predicted was too low. The prediction was too low because it's below because I've got a positive residual. Positive residual means my actual is above, predicted is below. And that's a positive residual. That is a common multiple choice question. If I have a positive residual, then I have which one is it? My prediction is too low. Negative residual, my prediction is too high because it's actual minus predicted. The predicted is underneath for this case, and so that's why it's too low. Okay, what to do with a quantitative bivariate data? So that's making a scatter plot, a linear regression equation. That's your y hat equals b naught plus b1x. Make a residual plot. Got to make sure your residual plots have a random scatter. If the regression equation has a pattern, try to straighten the curve. Now remember, in the AP test, you do not have to straighten the curve. The AP test does that for you. All you have to do is once it's straight, you have to evaluate because maybe it's now ln x and y, and you have to be able to know that it's the ln of x, not just the x. These are some patterns that you're supposed to know, but again, they're not directly on the AP test. You have them, but they're not directly on the AP test. All right, here, let's evaluate this here. Y hat equals 1.2x plus 31. Sorry about some of this. It looks like some of it came through kind of weird. But it says the regression equation, find the temperature of the top of Flat Top Mountain based on the temperature in Denver is this here, where X is Denver's temperature and Y is the temperature on Flat Top Mountain. Describe what the coefficients mean. So 1.2, that's my slope. And that means for every degree the temperature goes up in Denver, the temperature rises 1.2 degrees on top of the mountain. 31 is my y-intercept. And that means when the temperature in Denver is 0, the temperature on Flat Top Mountain is 31 degrees or protected on average. Or really should say, on average, but say the predicted. When it's 0, the predicted. Add that in there to temperature. R is equal to 0.87. That's my correlation coefficient. And the correlation coefficient says there's a positive linear correlation between the two temperatures. And you describe that with form, which it's always linear if it's a correlation coefficient. Shape. And for shape, you have either, not shape, but direction. And you have either positive or negative. And then strength. And you have strong, moderate, or weak are the choices for correlation coefficient. R squared. R squared is my coefficient of determination. And this is the one that we did when we had the counselors that guessed people's IQ scores. And remember, it was the percent of improvement over the average. The sentence you'll want to remember is, and actually it is, if you could please, on both of these actually, if you could look on your calculator, on your vocabulary, on your calculator, this is coefficient of determination, it's R squared, but this is the sentence that says the percent of the total variation in Y, which is my temperature on top, a Flat Top Mountain, is associated with the variation of X explained by my least squared regression line. So this sentence is on your calculator and your vocab. So remember this test how appropriate, the R squared test how appropriate your line is. Okay, making predictions for using the regression line. Anything outside of your domain, it is called extrapolation. So if this was from maybe 2 years to 5 years, let's say this is a height weight chart, I can't predict any weight outside of 2 to 5 years without it being called extrapolation. Just because two things are associated doesn't mean one causes the other. There may be a lurking variable that has an effect on both. We call this confounding. In order to have causation, we have to do an experiment. And in that experiment, we have to have a we have to have randomization of my treatments. Because it can't just be an experiment, it has to be a well-designed controlled experiment. And a well-designed experiment has randomization in it. All right. I'm going to stop here, and then another video will have these here, which has your FRQ, and then I have a PDF of your multiple choice. Well, I guess it's just one here. So thank you very much, and you can check the video. I guess it just has this one, but that's it. Thank you.